Welcome back. I hope you're having a wonderful Thursday and you're treating your guest teacher well. Um, Yesterday we talked about adding and subtracting polynomials, really just combining like terms. So today we're going to explore what else we can do with that. Um, so let's start with this 8.1. It says diagrams of products and explain why the diagram shows that 6 times 3 plus 4 is equal to 6 times 3 plus 6 times 4. Now you could easily say, well, Miss Womble, that's because of the distributive property, right? You distribute 6 times 3 and add 6 plus 4. But we could also think about it as these two rectangles over here on the side. One of them has side of 6 and another side of 3. So 6 times 3 gives us the area. 6 times 3, and that area is 18. And then we could look at the second rectangle, which has an area of 6 times 4. We multiply the side 6 and the side 4, and we get 24. Which matches if we think about 6 times 3 plus 4, that's 7. So 6 times 7 is 42, and 18 plus 24, whoops, I have another cat helper with me today, so if it looks like my pen is driving itself, it's because I've got a little cat helper. So both methods here, thinking about the distribution and using this area, thinking about these rectangles, gets us the same product. So question 2 asks us to draw a diagram to show that 5 times x plus 2 is equal to 5x plus 10. And I think we can use our example number 1 as a model. So I'm going to draw a rectangle here. And one side of that rectangle is going to have a side length of 5. So I'm going to write 5. And then the other side, x plus 2, I'm going to split that rectangle into two parts so that one part of it is x, and then adding 2 to that gives me the whole side length there. So notice I did write a plus 2. That's on purpose, and we'll see that a little bit later. And now if I were to actually think about the areas of those individual rectangles, well, length times width, again, 5 times x is 5x, and 5 times 2 makes 10. And if I add those areas together, I get 5x plus 10, which is exactly what we were looking for in the original question. So you're going to be seeing a lot of it and making a lot of these diagrams today, thinking about multiplication. So like I said, we're building off of our skills with adding and subtracting, and now we're thinking about product multiplication. So read this with me here in 8.2, drawing diagrams to represent more products. Applying the distributive property to multiply out the factors of or expand 4 times x plus 2 gives us 4x plus 8. So we know the two expressions are equivalent, and we can just do that over here really quickly. 4 times x plus 2, when we distribute 4 to the x, we get 4x. And when we distribute 4 to 2, 4 times 2 gives us 8. So it looks like that statement is true. We can use a rectangle with side lengths x plus 2 and 4 to illustrate the multiplication. So just like we did in our earlier example up above, we've got a side length of 4 and then x plus 2 there. So if we add those two lengths together, we get a rectangle with that side length, and then we can explore those individual areas. 4 times x gives us 4x. 4 times 2 gives 8 for the total area of 4x plus 8. So question 1, we're going to do question 1 together, and then question 2 I'm going to let you try on your own. It says, draw a diagram to show that n times 2n plus 5, so I've got n times 2n plus 5, and 2n squared plus 5n are equivalent expressions. So once again, I'm going to think about my diagram here. I'm going to make this diagram look a little bit different there. I'm going to put n over here on the side. And to represent my 2n plus 5, I'm going to do 2n, and then a 5 over here, right? That would be 2n plus 5. So I'm just going to indicate what all those pieces are with my highlighter here. And then I'm going to calculate those individual areas. So 2n times n makes 2n squared as my first area, right? N times n makes n squared, and then we're just multiplying by 2. And then n times 5 makes 5n, which goes in our other rectangle. And when we add those together, we get 2n squared plus 5n, which is exactly what we wanted in the problem. So question 2, it says you're going to use the distributive property to write an equivalent expression. Now, what that might have looked like in question 1 is we could have done that with just the distributive property, right? If we had done n times 2n plus 5, well, we're doing really the same thing. N times 2n gives us 2n, whoop, there's that cat, thank you, 2n squared, and n times 5 gives us 5n. So we get the same exact thing with the distributive property or with the diagram. So in question 2, you're going to start by just trying the distributive property. And if you get stuck, try a diagram. You get lots of space here. So I would pause the video and try these out on your own and come back when you're ready to check. Welcome back. So rewriting these, 6 times 1/3 n plus 2. Hopefully when you distributed, 6 times 1/3, that would have been perhaps one little sticking point, but 6 times 1/3 is 2, so we get 2n plus 12 there. For part B, when you distributed or made a diagram, you should have gotten 4p squared plus 9p, right? P times p makes p squared. In question C, we're actually distributing a 5 and r to both of those. So we get 5r squared. And then when we multiply, this is 5r times 3/5. And thinking about the order of multiplication, we can rewrite this in any order we want. We could do 5 times 3/5 times r. And 5 times 3, oops, not equals. 5 times 3/5 simplifies to 3. We get 5r squared plus 3r. And then the last example here, you may have chosen to rewrite this with the w out in front. Remember, with multiplication, we can put it in any order. But whether you did that or whether you just distributed both of those values to w, you should get 0.5w squared plus 7w. So if those didn't go quite as well, you might be a little bit stuck. Go ahead and check with a neighbor and see if their method of explaining might be more helpful. And when you're ready, we're going to go on to question 8.3. So we're trying to relate this back to our earlier work about quadratic expressions. And remember, a quadratic is thinking about that x squared. That's the big idea there. So you notice that we started to get some square terms. And so this is why we're relating this to quadratic functions. So here we go in question 1. It says this is a diagram of a rectangle with side lengths x plus 1, so x plus 1 there, and x plus 3. So x and 3, x plus 3. I like to have those plus signs written in between because it just helps me keep track of it and relate it back to the equation a little bit better. So you'll see me writing those in a little bit different than what's written here. Use this diagram to show that when we have this written this way, this is x plus 3 times, or excuse me, x plus 1 times x plus 3. And x squared plus 4x plus 3 are equivalent expressions. So basically, we're saying when we multiply these together, we should equal that expression over there. So we're going to apply the same logic, the same steps that we did before, but now we just have more rectangles to think about. So in the upper left-hand rectangle, our area is x times x, right? Or x squared. In our second rectangle on the top there, the area is going to be x times, we've got a length of 3 there. So I can rewrite that. X times 3 is 3x. Our next rectangle has an area of 1 times x, right? Because this side length x is also the side length down here. So 1 times x, we could just call it 1x. Oops, I wanted to do a different color. 1x. And then last but not least, this next rectangle, it has an area of 1 times 3. Again, those lengths, if it's 1 over here, it's 1 over here. If it's 3 up there, it's 3 down there. And so we get an area of 3. Now we have 4 small rectangles making up this big outer rectangle, right? This larger rectangle. So to find the area of the larger rectangle, we're going to add all of those smaller areas together. So x squared plus 3x plus 1x plus 3. Oh, just like yesterday, we had like terms. So that 3x and that 1x are going to combine here, and we get to simplify this just like yesterday. We get x squared plus 4x plus 3. And that is the equivalent expression that we were looking for. So it looks like we did it. So the area model really helps us kind of break down those steps instead of having to, keep track of what am I multiplying here. It really lets us break down. Okay, I may not be able to do this whole thing right now, but I can do x times x. I can do 1 times 3, and it lets us use those manageable steps. So once again, you're going to practice this a little bit more. There are 4 examples here in question 2. To write the equivalent expression. So you're trying to figure out, when I do this multiplication, what is that going to equal, just like we did in number 1. Now I want to set up number 2a together here. It's 5x plus 5 squared. Now you might see that square there and you're like, well, Miss Wumble, isn't this x squared plus 25 using the distributive property? Cool, right? Like that's easy. But I think we should still verify this. If we think about what it means to square something, right? To square something means to multiply it by itself. So we're multiplying x plus 5 times x plus 5. And so you're going to use that same strategy that we used up above, x plus 5 times x plus 5. So right now I'd like you to take a couple minutes here and finish up part A and then check out B, C, and D. You can work with a neighbor if you'd like, and then when you're ready, come back and check your work with me. Welcome back. So hopefully when you did this, you got x squared and 5x, and 25. So when you start to add those up, x squared plus 5x plus 5x plus 25, you actually get x squared plus 10x plus 25 because of those 2 like terms in the middle. This is not x squared plus 25. That's not the same thing if we have that 10x in there. So interesting observation there, just that the distributive property does not apply to exponents like it does to coefficients out in front. But let's check some of our other ones here. 2x times plus 4. So I'm going to do maybe just a little smaller one. Actually, a little bigger. 2x times x plus 4. So when I multiply, 2x times x gives me 2x squared. 2x times 4 gives me 8x. And when I add that together, I get 2x squared, 8x. Okay. Again, little box. Your box probably looks different. That's okay. That's really the best part about this is when we say an area, we don't really know what x is. So our diagram can look a little bit different. So we get 2x squared and 1x and 6x, and 1 times 3 makes 3. So 2x squared plus 1x plus 6x plus 3. Say whopping grand total. We've got some like terms in the middle there. 2x squared plus 7x plus 3. And then last one, you may have actually skipped D and started watching the video again, just maybe, because this one's definitely a little bit different. Instead of any actual values, we're given or letters in their placeholders there, little variables. But if I still make the same diagram, x plus n and x, oops, I meant to make that an m, x plus m and x plus n. Okay, x times x, I can do that, that's x squared. X times m, I don't know what m is. I'm just going to write it as mx. If it was a number, if it was like 2, that would be 2x. If it was 5, it would be 5x. So why not? Why not be mx? Same thing for my lower corner here. N times x is nx, whatever that is. And then n times m, well, I don't know what they are, but I know that m comes before n, and I'm going to be multiplying them together. So if I knew what they were, I would just do m times n. So when we string this all together to add our areas together, it's really important here that we identify that these in the middle are like terms. So this is actually something interesting. If you noticed that you might always be combining, some of those diagonals, that's a really good observation to make and something to hold on to for our work tomorrow. Those like terms are going to be valuable. But I'm actually going to leave part D like this, and we can explore that further tomorrow. Question 3 says, write an equivalent expression for each expression without drawing a diagram. So these are definitely a little bit more difficult to do without a diagram, but you may have a strategy in mind. As you were doing those earlier examples, you might have noticed something that could give you a strategy. If you feel like I didn't notice anything at all, Miss Wombled, that's okay. What I'd like you to do is I'd like you to give these your best shot for now, knowing that you're likely to make a mistake. So please pause the video, give it your best shot, and come back when you're ready to check. Welcome back. So doing this without drawing a diagram, it probably looked different, or it might have looked different from somebody across the room. But if it did this correctly, you would get 8x, x squared plus 8x plus 12 once you combined all of your like terms. And for your second expression, you would get 2x squared plus 20x plus 50. Now, if you didn't quite get these right, you tried it without drawing a diagram and it's just not right, that's okay. That's okay for today. I think this would be a really great time to go back and draw the diagram and verify that you can do it with the diagram. And tomorrow we will explore what is this strategy that lets us do it without a diagram. But honestly, in all truth, I think the diagram is a great way to go, and I'm never going to have you, I'm never going to tell you to do it without the diagram. We're just kind of adding to our toolbox. So either go back and try those with the diagram, or if you're ready, go ahead and open your practice assignment and get to work either by yourself or with a neighbor. And again, before checking your answers on Canvas, go through the whole thing, talk it out with a classmate, and then double check. If anything comes up, shoot me an email. Have a wonderful rest of